Hi everyone, Dr. P here, and in this lecture video we will take a look at molecular orbitals. Now, what are molecular orbitals? Well, molecular orbitals are another way of recombining atomic orbitals. Last time we saw, with Valence Bond Theory, hybrid atomic orbitals, where two or more atomic orbitals on a given atom are recombined to make new hybrid atomic orbitals. In this lecture, we'll look at combining atomic orbitals from different atoms to make new molecular orbitals. And one important thing to remember is that the number of molecular orbitals, or MOs, is equal to the number of atomic orbitals used. So let's look at an example. Let's look at H2. And we'll go ahead and we'll have some energy axis here. And we'll have a hydrogen atom with a 1s orbital. So it's going to look like that. And then we'll have another hydrogen atom with its 1s orbital. And that'll look like that. And then what we're going to do is we're going to combine these guys in such a way that they'll either add together and give us lower energy, or they'll add together and give us higher energy. And so we call this lower energy one the sigma 1s orbital. And the higher energy one we call sigma star 1s. So the little asterisk we call star. And now let's go ahead and put some electrons in here. Each hydrogen brings one electron to the party. So in the combined molecular orbitals, we will have 2 electrons in the sigma 1s orbital. And what that corresponds to is something that looks like this, where most of our electron density is in between the 2 nuclei. Up here at the top, if we had any electrons in this orbital, they'd look very different. It would look like that, with a node in the middle, a area of 0 electron density in the middle. Now, we refer to these orbitals that are lower in energy than our starting orbitals as bonding orbitals. And anything that's higher in energy than our starting orbital is an antibonding orbital. And bonding orbitals are going to stabilize things. Antibonding orbitals are going to destabilize things. And we'll only get the stability of a bonding orbital if we have electrons in the bonding orbital. And we only lose stability, get the destabilization of the antibonding orbital, if we have electrons in the antibonding orbital. So in H2, we can see here that we have 2 electrons in the bonding orbital and none in the antibonding orbital. So that corresponds to a single bond. In fact, we can write an expression for what we call bond order. And that is simply equal to 1/2 the number of bonding electrons minus antibonding electrons. Okay. Now we could do this for other atoms if we wanted to, or other molecules, I should say, if we want to. So just to again review everything that we've got here, we've got our starting 1s orbitals for each hydrogen atom. We combine them to make two new orbitals. One is lower in energy, more stable than the original. One is higher in energy. And then we take our total number of electrons and start filling from the bottom up, filling up our molecular orbitals. In this case, our bonding orbital, the sigma 1s orbital, has 2 electrons in it. And we have no electrons in the sigma 1s star antibonding orbital. So our bond order here is equal to 1. And that corresponds to a single bond, or in valence bond theory, a sigma bond. All right, let's look at a few more examples here. And the text goes into some detail. I'm going to go into some detail as well, just to illustrate a few points here. I'm not going to draw every diatomic potential molecule from the first row, but we'll go ahead and get started here. So let's look at helium-2, question mark. Can we get helium, a dihelium molecule? So here's our energy, and we'll start with 1s and 1s. And we'll combine, and we'll get our sigma 1s and sigma star 1s. I like to draw in these little dotted lines to sort of connect things so that you can tell where the molecular orbitals came from. So like we can see the sigma s came from the 1s from each atom. When we have more atomic orbitals that we're combining, it helps to keep track of where things are. Now, of course, helium brings 2 electrons to the party. Well, it tends not to party because it has full 2 electrons. And if we then try to put 4 electrons in our orbitals, we see that we now have a full antibonding orbital. So here our bond order equals 0. Okay, and that's analogous to no bond forms. No bond forms. Which is why we don't see He2 molecules anywhere. We don't see dihelium molecules. Now, could we get a dilithium molecule? Regardless of whether or not you're in Star Trek. That's their supposed rare material used to help run the warp engines in Star Trek. And anyway, dilithium crystals. So let's see, could we get dilithium? Okay, we have 1s orbitals are combining. And so we get a sigma 1s, sigma star 1s, and then our 2s orbitals are also combining to make sigma 2s and sigma star 2s. And now lithium has a total of 3 electrons, 1, 2, 3. 1, 2, 3. So we can fill these in then. We've got 6 total, so 4 down here. 1, 2, 3, 4. And then up here on the the second level here, we've got 2 there. So now our bond order equals 1/2 of 1, 2, 3, 4, 4 minus 2. Because we've got 1, 2, 3, 4 bonding electrons and 2 antibonding electrons. Excuse me. Now, so this bond order ends up equaling 1. It's 1/2 of 4 minus 2. 1/2 of 2 is 1. Now, if you pay attention, you notice that these electrons here essentially cancel each other out. And so this area here are our core electrons. And really, they're not going to be participating in bonding. We really only want to look at the valence electrons, so we can ignore those 1s electrons. So anything below the valence shell, we don't usually have to worry about. All right. So that's some simple diatomic, not simple, but those are some diatomic molecules. We saw H2 has a bond order of 1, so it forms. He2 has a bond order of 0, so it would not form. And then Li2 has a bond order of 1, so in theory it could form. Now we can go ahead and do this for beryllium, boron, carbon, nitrogen, oxygen, fluorine, for the whole rest of the second. We can do this for the whole rest of the second period. I'm not going to do that, but I am going to show you what the orbital diagrams look like when we bring in the p orbitals. So we'll have our energy here. And of course, we still, have our 1s. Giving us sigma 1s and sigma star 1s. And then we'll have our, up a bit higher, we'll have our 2s. And we have sigma 2s and sigma 2s star, sigma star 2s. And then we have our 2p orbitals. And we have 3 of them. And so we can get things in different combinations here. So we could get a sigma 2p orbital. We can also get a sigma star 2p orbital. But then we can get some orbitals that are a bit lower in energy, or just a bit higher in energy. And these are the pi 2p orbitals and the pi star 2p orbitals. And so this is what things look like for O2 and F2. In fact, if we wanted to, we could fill this in for oxygen. So oxygen has the 2 core electrons, so 1, 2, and then 6 valence electrons, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Those are, I counted the core. I don't need to count the core. So 1, 2, 3, 4, 5, 6. Hopefully you guys can see that in there. And now let's go ahead and combine and fill in our molecular orbitals. So our sigma 1s and sigma 2s orbitals and the sigma stars for those are completely full, so these aren't going to contribute to bonding. So I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons. So let's put those in. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and remember, electrons spread out before they pair up when we're putting electrons in orbitals. So this would have a bond order of 1, 2, 3, 4, 5, 6 minus 2, which would be 4 divided by 2. So here our bond order for oxygen. Now, just as an aside, if we draw a Lewis structure, we're pretty tempted to draw this for O2. Okay, we have 6 valence electrons, so that's a total of 12, 2, 4, 6, 8, 10, 12, and we have complete octets. But if we look closely here, if we look in here, we see right here we have unpaired electrons. And so these unpaired electrons give water some interesting properties. We say that that water is paramagnetic. It actually can be affected, sorry, not water, oxygen is paramagnetic. It can actually be affected by a magnetic field. And so our Lewis structure is not accurate. We'll say doesn't show unpaired electrons. Okay, and it's kind of, sorry about that, my phone is dinging here. Let me just silence that. It's always good to silence your phone. Anyway, so the molecular orbital theory, the upshot is the molecular orbital theory comes up with oxygen O2 having unpaired electrons, which is consistent with what we see with the properties of O2, the magnetic properties of O2. So something like valence bond theory and Lewis structures don't accurately represent all of the aspects of these molecules. Okay, so I realize this is quite a bit. Don't worry, I'm not going to make you draw these, but I may make you fill them in. I'll provide them for you, and I may make you fill them in. Now, we could have a slightly different version, and this is for B2, C2, and N2, diboron, dicarbon, dinitrogen. And what we see here is something called PS mixing. And so let's go ahead and take a look at N2. Excuse me. And we'll see that the lower energy levels are going to look the same. Sigma 1s, sigma star 1s, and then we'll have our 2s, and our sigma 2s, and sigma star 2s. And then we'll have our 2p orbitals, 2p, 2p. But now we actually have the pi 2p and the sigma 2p are switched. So we actually get our pi 2p is lower in energy than our sigma 2p. But we have the same up top that we did before. With our sigma 2p star and our pi 2p star. So let's fill this in for nitrogen. Nitrogen has a total of 7 electrons. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And now I can fill in these electrons here. And I've got 1, 2, 3, 4, 5, 6. So let's put those in. 1, 2, 3, 4, 5, 6. So now our bond order equals 3. Sorry about that, it was off screen a little bit. 4 and 2. And that corresponds to a triple bond. Also, we have no unpaired electrons. We call those types of molecules diamagnetic. And so nitrogen is not affected by a magnetic field the way that oxygen is. So I do want you to be able to fill in these types of diagrams if I provide you with the diagram. All right, now let's see what else I wanted to talk about. Oh yeah, the Lewis structure here is N, triple bond N, like so. And that's consistent with the molecular orbital picture. So in this case, both the Lewis structure and the molecular orbital picture give us a pretty accurate representation. Now, what if we had different atoms bonded together? So instead of O2, H2, N2, what if we had, I don't know, NO? Let's take a look at NO. NO was Molecule of the Year back in 1995, 96, something like that. So we call these types, put that back there. We call these types of molecules heteronuclear diatomic molecules. So we could have similar atoms, for example, NO, in which case because the atoms are similar, we're actually going to get a diagram that's similar to one of these for the diatomic. So the closer they are in the periodic table, the more likely they are to have the same looking molecular orbitals, I should say, the same looking molecular orbitals. So I've got my sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, and then we'll have the sp mixing, or ps mixing. So we have our pi 2p, sigma 2p, and then pi 2p star, and then sigma 2p star. And now for NO, let's just look at this, for example, in Lewis structure. I've got 5 electrons from nitrogen and 6 from oxygen, so I should have 11. Oh, I need an unpaired electron here. Well, how do I know it's that and not that? Well, I don't. But let's go ahead and fill in our valence electrons here, not our valence, our molecular orbital electrons. So I'm going to have 11 from this point on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And once again, we have an unpaired electron. That guy right there. And so if we count the bond order here, our bond order is 2.5. And so these Lewis structures really don't accurately describe, because in a Lewis structure you're trying to assign electrons to atoms, but in this case this unpaired electron is sort of spread out over the whole molecule. Remember, electrons can be thought of as diffuse clouds of probability, so these aren't really accurate here. But the molecular orbital picture does predict and show that NO would have an unpaired electron. And if we have a single unpaired electron, we call that a free radical. And free radicals can be very reactive, especially doing oxidation reactions. Okay, now what if we had different atoms? And not just different N and O, but very different atoms. So HF, fluorine is much more electronegative than hydrogen. So maybe I'll say very different atoms. That's my energy here. So now, if I draw this diagram here, I'm going to have my hydrogen, which has a 1s, and then I'm going to have on the other side my fluorine, and it turns out the energy of the fluorine is way down here, one of my 2p orbitals. So I take a 1s orbital and I take my 1 2p orbital that only has one electron in it, and I'll go ahead then and come up with this very distorted molecular orbital. So I've got my sigma and my sigma star, and hydrogen brought one orbital to the party, and this 2p brought one electron to the party, and this 2p orbital brought one electron to the party. So I have 1, 2 electrons. So my bond order equals 1, and this can also sort of explain, and I want you to think about this can also sort of explain or is consistent with the electronegativity that we observe, where the electrons are more concentrated, or where there's more electron density in the chemical bond. Remember, fluorine's more electronegative, so it pulls electron density towards it. And this type of diagram actually helps explain that as well, because the occupied molecular orbital is awfully close in energy to the fluorine atomic orbital. So that means that they are more similar. All right. Phew. Now, one more thing to talk about, and that is, when do we use molecular orbital theory? Why do we use molecular orbital theory? Well, let's take a look here. And we're going to use molecular orbital theory when we have to. So let's combine VBT and MO models. So one thing to note is that the sigma molecular orbitals are very similar to the valence bond theory sigma bonds. So what that means we're going to do is we'll use valence bond theory and hybrid atomic orbitals for sigma bonding. And then we'll use molecular orbital theory for pi bonding. And this works pretty well. An example is C6H6 benzene. Okay, and so with benzene, we'll have our energy here. And there are 6 p orbitals that contribute to the what we call the pi system. They overlap and give those pi bonds in valence bond theory. And we talked about how everything overlapped, and it's like the resonance structure. And well, with molecular orbitals, we would see that those 6 p orbitals combine to give us 6 molecular orbitals. We have pi 1, pi 2, pi 3, pi 4 star, pi 5 star, and pi 6 star. And then there are 6 electrons, one from each carbon, that are participating in that bonding. So 1, 2, 3, 4, 5, 6. So this is just the pi electrons. And we can see that all 3 bonding orbitals, so we've got anti-bonding up here, and we have bonding down here. All 3 bonding orbitals have electrons in them, and none of the anti-bonding orbitals have electrons in them. Thus, benzene is very stable. And so molecular orbital theory provides us a way to explain the stability of benzene, that otherwise we have to do things like invoke resonance structures, which are really a man-made concept. And the molecular orbital theory, although it's also man-made, is more accurate for describing these more complex pi systems. So, take-home message is use valence bond theory for sigma bonding, and use molecular orbital theory when you have to for pi bonding. All right? Okay. Well, that's it for different types of bonding. There will be one more lecture video that I will record on molecular polarity, because I did not talk about that with chapter 7. But I do want to give you guys a little lecture on molecular polarity, so you can watch that. But in the meantime, stay safe out there. Bye now.